All right, we're going to continue on in chapter 9, this time starting with adding water across a triple bond. Now, this one is a little bit different. You're really going to want to practice with this one. When we take an alkyne and we add water across it, we're not actually going to get an alcohol. We're going to wind up getting either a ketone or an aldehyde. And we're going to talk about the reasons for that, right? So adding water. Now, we're not going to see acid catalyzed hydration exactly. We're going to have a Markovnikov and we're going to have an anti-Markovnikov addition, but the reagents are going to be a little bit different. All right, so let's start off with Markovnikov. It's sort of like acid catalyzed and oxymercuration, demercuration had like a baby. Okay, so you're going to take still your acid, H2SO4 and water. So it is acid and you of course have water, we're adding water, but you're also going to have mercury sulfate. So anytime you're seeing mercury, you should be associating that with Markovnikov addition. If you have a terminal alkyne, that'll make a difference. You're going to add the oxygen, right, to the more substituted side. But instead of getting an alcohol, you're going to get a ketone. The alcohol intermediate isn't stable. So what you might initially think of is, okay, alcohol to the more substituted side, right? If there's a hydrogen here, hydrogen to the less substituted side. This is called an enol, right? Because you have an you have a double bond with an alcohol on it. This is not, it's not stable. You can't isolate it. It is going to rearrange itself into an enol. This is called tautomerization. It's a very specific kind of isomer when you look at the enol versus the ketone. It is the same chemical formula, but it is a constitutional isomer, but it is very specifically only different in the placement of a double bond and a proton, right? Tautomers are just a very specific kind of constitutional isomer. You do not need to know this mechanism, but you will need to know the mechanism for a tautomerization. You cannot keep this from occurring because it only takes a very okay, so again, you don't need to know this one. It only takes a very small amount of acid or base. So tautomerization can occur as an acid catalyzed or a base catalyzed condition. And if you're working with glassware, there's always some protons stuck to that glassware. You cannot get away from this. And so the tautomerization is going to happen. You're never going to be able to stop at the enol. So if we look at acid catalyzed, it's two basic steps. And acid catalyzed versus base catalyzed, it's which step is first and which is second changes. All right, so if we have acid around, right, and we've got hydronium to show our acid, you could just put H plus as well. We are going to start off by picking up that proton, right? We've seen our alkene act as a base before, and it does that here as well. That is going to give us a carbocation. That carbocation has a resonance structure with that oxygen, right? Because there's a lone pair next to a carbon with a plus charge. So the other resonance form, right, puts that plus charge on the oxygen. This is acid catalyzed, so we get our acid back, right? The water picks that proton up. This is called a solvent-mediated proton transfer, right? The solvent is helping us move those protons around. Now, in base catalyzed, and that's not shown here, but we're going to look at it anyway. Starting with your enol. Now, if you have any base around, right, in the first step in acid catalyzed, you reacted with the double bond, and then the second step was you removed that proton. Well, in base catalyzed, we're going to go in the opposite order here. Let me alter this a little bit to show the actual bond. Your base is going to deprotonate first, and since we're in base, instead of a plus charge, we're going to have a minus charge, but it's an allylic negative charge, so we do have a resonance structure here where our double bond is formed and our negative charge is shared on that carbon. Now, we've made water. We don't have acid, so we don't want to show acid, but this protonation is going to come from the water. We get our base back, hence base catalyzed. All right, so no matter what we do, acid or base, you are going to get this tautomerization. You should know this mechanism, and you should be able to predict your products. All right, so if you've got, there we go, an asymmetric double bond, and you use sulfuric acid, water, and mercury sulfate, you are going to make a ketone. But what if we want to go to the less substituted side? Well, of course we have an answer for that. It's hydroboration oxidation. Now, this looks very, very similar, if not identical, to the reagents in the alkene reaction. There we go. But something you may notice is you may find that there is, let me see if it's on the next slide. No. You may find that there's R groups. It may be Br2H. You're really just focusing on that boron again. It may have THF included, might not. The second step should be identical, though. You're going to have a hydroxide and a peroxide. And you are going to make the anti-Markovnikov addition. Instead of it being an enol, it is still going to tautomerize using the same mechanism we saw with the ketone. It's just going to make an aldehyde because it's going to be on the end. There's the base catalyzed tautomerization mechanism. I'm not sure why that came second. I guess because this one is in base. Yeah, of course, that makes sense. You don't have to know this mechanism. You didn't have to know it for alkenes. It does add sin, but it doesn't matter. You're not going to wind up with a double bond there. Here are some of the other boron reagents that could be used. These bulky alkyl groups can be useful for this reagent. For this reaction. But you don't need to have them memorized. Remember, what you're looking for is that boron. Right, so here's another way it may be written. Dicyamyl borane. And then the second step, of course, is the peroxide and hydroxide. You need to practice predicting the products. Anytime we deal with triple bonds, make sure you're counting those carbons. One of the most frequent mistakes I get here is people will lose or add carbons when they shouldn't. So we have control of our regiochemistry. So there's two more reactions that you need to know. The tautomerization is the only new mechanism so far in this section. We're going to move on to halogenation next. Right, so that's going to be taking our alkene and reacting with excess halogen, right? We could put excess here. You could use one equivalent and get it to add once, but this one is kind of hard to control. So we're going to stick to focusing on the excess. You're going to add the halogen across the double bond twice. So you are going to wind up with 4 bromines or chlorines on your carbons that were in your double bond. Now, the CCl4, this is just solvent. This is just a non-reactive solvent. It does start off by just adding once. It makes the major product that is anti, but you make both. I'm not going to ask you about one equivalent. I will stick to the excess full reaction. Ozonolysis. This is another one that we saw with alkenes, but it's going to be a little bit different with alkynes. So we'll start off with an internal alkyne. The reagents are very similar. Go O3, but instead of DMS, this needs even a less reactive reducing reagent. You can just work it up with water. It is still going to cut through that triple bond and oxidize those carbons, right? Increasing bonds to oxygen. So let's say this is R1 and R2. Because it doesn't have to be symmetric. You are going to get all 3 bonds to oxygen, which is going to leave you with carboxylic acids. And just depending on what those R groups are, you'll get 2 equivalents of a carboxylic acid, or you'll get an equivalent of 2 different carboxylic acids. Now, if you have a terminal alkyne, you are going to wind up making some CO2. Right, because you're still going to cut this down the middle. And if there is an R group on one side, you will make a carboxylic acid. But the side that has a hydrogen, it is going to fully oxidize that. It is going to replace all bonds to bonds with oxygen. So you will make some CO2. So with with alkenes, you could make an aldehyde or a ketone. With alkynes, you make carboxylic acids and potentially a carbon dioxide. You do not need to know the mechanism of this one either, but you do have a lot of reactions that you need to be able to predict products for and have the reagents memorized. There should be some practice up on eCampus for you, including a new spider diagram. Okay, so this is a symmetric alkyne. So if we do ozonolysis, we should get 2 equivalents, right? A 5-membered ring, 1 carbon here, OH. So you're going to make 2 of these.